Hello, this is Dr. Liu. In this video, we have two examples of conservation of energy with springs. So let's start with the left side. And this example came from a University of Physics published by OpenStax, Chapter 8, question number 74. An object of mass 10 kilograms is released at point A, slides to the bottom of the 30-degree incline. So here it is. Then collides with a horizontal massless spring, compressing it to a maximum distance of 0.75 meters. See below, it's right here. The spring constant is 500 newtons per meter. By the way, that is very stiff. The height of the incline is 2.0 meters. And the horizontal surface is frictionless, which means this inclined plane is not frictionless. So we have questions A through D. Question A, what is the speed of the object at the bottom of the incline? So this has nothing to do with the spring. It just has come down the inclined plane. We can use energy conservation in a more general sense, so that the original mechanical energy minus the absolute value of the work done by friction is equal to the new mechanical energy, right? So that can be done that way. B, what is the work of friction on the object? Well, it is on the incline. Okay, so we need to find that. And then C, the spring recoils. Okay, so that is, finally the object is interacting with the spring. So the spring recoils and sends the object back toward the incline. What is the speed of the object when it reaches the base of the incline? So coming back. And then what vertical distance does it move back up the incline? So that means, again, where the object is moving against friction. Friction takes some energy away, again, not giving it back. So this is a relatively long question. So let's start with making some definitions of these different points in time. I like to call them snapshots. So here is snapshot 1, which is the object is at rest, is released at the top of the inclined plane. So now it slides down to the bottom of the inclined plane, and this is a 2, which means it has gone down the inclined plane. There's no more friction, and 3 is, well, you can say that it encountered the spring, but since there's no friction, 2 and 3 will be the same, right? So I would like to say that 3 would be, here's that spring. I didn't really count how many coils, but this is compressed. And the object is at rest. So that will be 3. And then 4 will be, it recoils and pushes the object back out. So I can maybe draw it here. So it pushes the object back out. And there's even a 5. So when the object slides along the horizontal plane, it doesn't lose any energy. There's no friction. And then it comes up the inclined plane and somehow stops somewhere short of the original height because of friction, right? So this will be a 5. So let's go through this once again. The object at rest, released, that's 1. Coming down to this point, it's moving with a speed as 2, and then it compresses the spring and maximally compresses it until it stops momentarily. That is 3, and then the spring recoils and pushes the object back out, losing contact with the object. That's 4, and as the object travels back along the horizontal plane, it doesn't change its mechanical energy, and then it slides up the inclined plane and stops here. That is 5. Okay. So between 1 and 2, we can use energy conservation if we count the work done by friction. So let's see. We want to just say that energy, mechanical, is equal to, there are 3 parts, right? So kinetic energy plus potential energy, and the potential energy has both gravitational and the spring. And now you may have realized they do not change during the same process. So when the gravitational potential energy is changing, spring's potential energy it isn't changing. So this is why I picked this as the first question, because they don't change at the same time. So we have 1/2 m v squared plus gravitational potential mgy plus spring potential energy 1/2 k x squared. So the x will be starting from here, and let's just say it points this way and indicates the spring compression. And the y will be starting from the bottom, the inclined plane. Grab a ruler. It would point upward, so that we start with a y equal to 2 meter y1. Okay. So here's our complete mechanical energy expression. So now we can say that E1 is, I will do this once or twice, mv1 squared mgy1 plus 1/2 k x1 squared. Since there's no spring compression, no initial speed, we can set the first term and the third term to 0, and only the second term is a non-zero term that involves the 2 meter height. So we'll do that. 1/2 m0 squared plus mgy1 plus 1/2 k 0 squared. So we end up with just mgy1, and let's plug in the numbers. 10 kilograms, 9.8 meters per second squared, 2.0 meters. So that's 196 joules. So just multiply 9.8 by 2, and that's 19.6, and then move your decimal place to the right. That's times 10. So we have the complete knowledge of how much mechanical energy the system starts with. So let's move on to mechanical energy 2. So now we'll have all these terms. Now we're down here. We have velocity, we have 0 height, we have 0 compression. So it is 1/2 mv2 squared. I'm skipping this whole thing. So 10 kilogram and a half, so 5 v2 squared. Okay. So let's keep on moving to the right and compressing all the way. So E3. We don't have any kinetic energy. We're momentarily at rest. We don't have gravitational potential energy because we're at the bottom. This is not exactly at a height. I just can't really draw it well, overlapping each other, right? So I have to do it that way, just kind of stack them up. This is still at 0 height. That's also at 0 height. Okay, so we only have the 1/2 k x3 squared. And according to the question, compressing maximum distance 0.75 with a 500 newtons per meter. So this is 0.5 times 500 times 0.75 squared. So let's use our calculator. Okay, so let's get Python. We have let's grab a keyboard. So we have 0.5, 500, 0.75 squared. So 141 joules. Apparently we have lost some energy here. So 141 joules. Let's vanish calculator. Okay, so let's move on to the snapshot 4. Now the spring has been completely decompressed, so there's no more spring potential energy. Also, the height was still at 0, so it's only a kinetic energy of the moving block. So E4 is 1/2 m v4 squared, and we only know the mass, so it's 5 times v4 squared. And then coming up the inclined plane and stopping, that's E5. So E5 is well, we have 0 velocity, we have 0 spring compression. All we have is gravitational potential energy. So mg by 5. 10 kilograms times 9.8 by 5. So we have 98 by 5. Okay, so from 1 through 5, we have all the different mechanical energy terms figured out. So here's 1. This is completely known right here. And then after sliding down and losing some energy, mechanical energy to friction, it has this much. And then compressing the spring and stopping, it has this much. And being pushed back out, and then it has this much. And then it climbs up the inclined plane again and stops. It has this much. Okay, so which parts are following energy conservation? Well, we know that between 2 and 3, right, the block, the object is no longer on the frictional surface. So over here, 2 and 3 here, we can connect them with energy conservation, right? So this to energy conservation. So that means E2 equals E3. And from there, we can find out how fast the block was after it slides down the inclined plane. Okay, so we can do that. And E3 and E4, they can be connected because that also does not involve the frictional surface. So we can do E3 equals E4, and then we can find out how fast the block is. And I assume that would be the same as this, because it's just like getting pushed in for the spring and then pushed back out without changing energy. It would be the same. So then between the 4 and 5, then friction should do some work. Okay, so let's go ahead and list our equations. So energy is conserved between 2 and 3. So there's no friction. Horizontal surface. All right, so let's do that. We have the 5 v2 squared equals E3 is 141 joules. So V2 is equal to 141 divided by 5 square root. Okay, let's pop out our calculator. We have 141, but okay, let's use this keyboard. So the underscore represents the last answer, the 141 over 5. Then raise the power of 1/2. So we have 5.30 meters per second. Okay, so this is how fast the block was at the end of the incline. Okay, we can also do the 4. So E3 equals E4. That's the same reason, no friction on the horizontal surface. Let's see if I can borrow this reason. I think I got one of those strokes. Well, everything except for one of the strokes. The horizontal stroke on the friction is here, but no. Okay, so no friction again, right? And we have the exact same expression, except this side, this is 141 side. The other side is that 5v4 squared, right? 5v4 squared. So we'll naturally get the same exact thing as v2. So 141 over 5, and we still have 5.30 meters per second. Okay, so we're done with mechanical energy conservation. The next part should be looking for this more generic sense of energy conservation. Okay, so looking at our answers compared to the questions, we answered part A, the speed of the object at the bottom of the inclined plane. That would be speed of 2, right, v2. So we got that, 5.3. And what is the work of the friction? Okay, so we can do that. We can say that between 1 and the 2, 1 has more mechanical energy than 2 because friction doesn't work to take energy away. So let's assume that this is friction's work less than 0. So we can say that E1 plus work by friction is the same as subtracting a positive number that equals E2. Okay. So work by friction is equal to E2 minus E1. And according to this, E2 and E3 are the same. That's the same as E3 minus E1. And they both have numerical values pretty conveniently listed here. So 141 minus 196. That's a negative 55 joules of energy. So friction did 55 joules of negative work that took this much energy out of the block. Okay, so that was that. And the spring recoils, and what is the speed of the object when it reaches the base of the incline? So that we answered in here, the speed 4, so that just bounces out, and then there's no speed change across this frictionless surface. So we only have one last question, what vertical distance does it move back up the incline? So you could have one of these two separate approaches. One of the approaches that I prefer is looking at this amount of work done, and I could evenly spread it out across the entire inclined plane's motion. I have a 30-degree angle and 2 meters. So this incline actually has 4 meters long. So within 4 meters, friction did this much work. So we can calculate how many joules per meter work. And then as it comes back up, there's no reason that it does a different amount of work per meter. At least we weren't aware of that. So we can do that. And another way you can do is try to find out frictional force. Because you have the mass, you have an angle, you can analyze all the forces, but you end up, well, you conclude the same exact way. You found out friction, but that's not entirely necessary to go the long route. So let's do the short routes. We know work done by friction is this, and incline. So we have an L length along the incline. It is the height, so y1 divided by sine of 30 degrees. So why exactly is this the case? So y1 over the L, that is opposite over hypotenuse, that's a sine 30 degrees, right? So we have that, and then if you divide out sine, if you multiply the L, then you get this. So the inclined plane L is equal to 2 meters divided by 0.5, that's sine 30. So we get 4 meters. So this is the length. Okay, so let's move on to the right half of this portion. So we have work done by friction equals frictional force times a displacement. So this will be the L, and time the angle, cosine of the angle between frictional force and L. This is apparently 180 degrees, right? The L is displacing downward and friction points upward. So 180 degrees cosine gives you a -1. So this is a negative frictional force times the length of 4. So the -1 came from here. This cosine 180 equals -1, right? And according to our calculation, work done by friction was this amount, so minus 55 joules, and the other side also equal to friction's work. So we conclude frictional force has this amount of 55 over 4. Let's calculate that. Hmm. 55 over 4. So 13.8 newtons of frictional force. Okay, so now we have friction. We can calculate how much work is done on the way back up. So let's call that incline L5. So a length upward, right? And this L5 is going to be related to the Y5 divided by sine 30 degrees. All right. And we have what we have here for the energy 5. We actually have this energy 5 here. And let's say that energy 4 plus work done by friction, this is between 4 and 5, right? Between the bottom and up, back up the incline. So how about we put here 4 to 5, just to indicate this is a different amount of frictional work done than over here, that is from 1 to 2. We could have put a 1 to 2 here, but now we realize we need that to make these two separate quantities. So going up the inclined plane, losing some energy, and now I get to E5. Right, this is a negative quantity. So E4, according to this, is this quantity, and also that's also equal to E3. E3 has this numerical value of 141. So 141 plus work done, so frictional force times L5 and times cosine of angle between friction and the displacement. Again, it is 180 because displacing upward, friction points downward. So that's again 180. And that's equal to E5. E5 is 98 Y5, so 98 Y5. Alright, so we have 141 plus frictional force was 13.8, and L5 can be replaced with Y5. So Y5 over sine 30 degrees, over a half. So let's move along and get this in a better format. Over 0.5 is the same as multiplied by 2. Okay, so now L5 can be replaced by twice Y5. And here this is a -1. Again, 180 degrees. Friction always counters the relative displacement. So that is equal to 98 Y5. So one more step. Here's a negative. So 13.8 multiplied by 2. Let's use our calculator for that. Because we have 13.75, we can multiply that by 2. That's a little more precise. So 27.5. 27.5 by 5 equals 98 by 5. So now we can add 27.5 by 5 on both sides to move by 5 to one side. So 141 equals 27.5 plus 98 y5, and that makes y5 equal to 141 divided by that sum. So let's try to do this with an eyeballing. Okay, 9.98, that's 100. So 127.5, 125.5, because we're too short of 100. So let's calculate 141 divided by 125.5. So we have a height of 1.12 meters. 1.12 meters. Alright, so let's do a little bit of bookkeeping. We want to move this just a bit to the right to make them line up a little better. I think this is a bit past the center line. So let's kind of tuck it in, times 4. Okay, so what this question did was it was rather complicated. There were many different energies, but what is clear is we're following this recipe. There are 3 terms for mechanical energy, and at each point in a snapshot of energy, we're writing it out with all the 3 terms, looking for their values. Some of them may be 0, such as at rest or not compressing a spring. Right, so we're writing them down, and then we're analyzing in between which energy snapshots we can use mechanical energy conservation, between which snapshots we can use a more general version of energy conservation, including the work done by friction. So all that worked out with all the answers, and this is the next question we have. It involves the spring potential energy and gravitational potential energy simultaneously. At the same time, they're changing because as the spring is decompressing, the ball is rising in height. So the height will actually be involved in both spring and gravitational potential energy. So let's take a look at the question on the right side. This is also from University of Physics, Chapter 8, question number 43. The massive spring of a spring gun has a force constant K equals 12 newtons per centimeter. Okay, so this is not necessarily much weaker than the other one because this is per centimeter, so it's actually 1200 newtons per meter. It's actually stiffer than the other one. So now when the gun is aimed vertically, a 15-gram projectile is shot to a height of 5 meters above the end of the expanded spring. See below here. How much would the spring compress initially? So let's think about this. We have 3 different parts of energy, mechanical energy. Again, there's kinetic, there's gravitational potential, there's also this spring compression potential energy. So we'll start with enumerating all the terms of mechanical energy. So kinetic energy plus potential energy, and that translates into 1/2 mv squared plus mg, whether it's going to be a y, and also a compression. Because the spring is vertical, we can repurpose the coordinate as the spring's compression, but we need to be careful over here because as the spring is no longer in contact with the ball, and the ball gains a certain height, the spring's compression should be 0, right? So this is a bit tricky here. So let's still keep it as x, and we'll relate x and y in different situations. There's 3 different points in this problem, and let's assign some energy snapshots. So this is pretty easy. That's a 1. This is a 2. This is a 3. So during 1, there's no kinetic energy. There's gravitational potential energy and a spring potential energy. And then in 2, there's kinetic energy, right? There's no spring potential energy because the spring has relaxed. There's gravitational potential energy. And then the 3, there's no kinetic, and there's gravitational potential but no spring. So I think we can start from anywhere with the vertical height. But if I start from here, for example, I will avoid having any negative gravitational potential energy that can confuse people. And we can do that just by setting our axis to point up from right here, from this height. So let's use a ruler. So here's our y-axis. This is our origin here. So the spring compression. Okay, so this is that D there. Good thing they gave us a symbol. Otherwise, we will have to define a symbol. So let's start by describing mechanical energy at snapshot 1. So again, just like I did before, I will enumerate all the different terms at least one time. Okay, so we're at rest. There's a zero speed, and we're at zero height. There's a zero gravitational potential energy, and we have a compression. The compression amount is d, so 1/2 k d squared. So this results in a just 1/2 kd squared. So 1/2 times 12 newtons per centimeter, and we want some standard units, and centimeter doesn't really work too well. So this is in the denominator. We can do 100 centimeter on the numerator, divide by 1 meter to get rid of centimeter, and then we also have this d squared. Right, so E1, this is 1200, and let's see, 1200 we have divided by 2, 600, and we have d squared. I know that we also have the Newton per meter in unit, but that's okay. We're using all the meters and newtons and joules, so there's no need to mention it at the moment. This whole thing's unit is joule anyway. So now we have this energy, and let's move on to E2. Okay, so for E2, the spring has relaxed. There's no more spring potential energy, but there's some gravitational potential energy and the mechanical and kinetic energy. So 1/2 m v2 squared plus mg. This height is specifically called d, so mgd, and n plus 0. So we'll still write it out. K0 squared. No more compression. So this is equal to 1/2 m v2 squared plus mg d. Okay, we don't really know d, and we have some we have no idea what this number is. The mass we do, but why plug it in, right? So this is already good enough. We can move on to the third one and see what we can find. So the third one says this E3 is equal to no more kinetic energy. So let's write it out as m0 squared. And the height is this is d, right? So this is 5 plus a d, because that is our reference height, the origin, right? This is a d, and this is a 5 plus a d. So mg 5 plus d. And spring still has no compression whatsoever. Spring's job is done. So now we're left with zeros and this one alone, mg 5 plus d. Okay, and in this question there's no mention of friction anywhere, so we can assume that friction doesn't exist. So then in between 1 and 2 we have mechanical energy conservation, and 2 and 3 we also have mechanical energy conservation. So we can use E1 equals E2, and then separately E2 equals E1, or E1 equals, well, E2 equals E3, whichever. There's 2 versions of them, right? 2 out of 3. So what I'm interested in is basically looking here. E1 involves d, and E3 involves d, and the rest of them are known quantities such as mass and gravity. So if I equate 1 and 3, I can solve for d. So once I solve for d, the total energy becomes a known quantity. And then if I equate that known quantity to E2, and with a known d, I can solve for the speed, right? So although the speed was not really mentioned, it's a useful answer. I would ask for it. So let's do this, E1 and E3. So E1 equals E3. This gives us 600d squared equals mass is 15 grams, so 0.015 kilograms times 9.85 plus d. Let's use our calculator. .15 times 9.8, so that's 147. If I just multiply this by 5.735, 147 and 735. So okay, so what we are ending up getting is a quadratic equation in D. So let's get this quadratic equation out. So 600d squared minus 0.147d minus 0.735 equals 0. And since this value is so small compared to the 600, I would expect that the d will be, the two different d's will be very easy to tell which one we would pick. So let's use our calculator again, because our calculator has a quadratic equations solution routine. So let me bring out my keyboard. Okay, so a value is that quadratic coefficient of 600, and b value is a linear coefficient minus 0.147, and c value is that constant minus 0.735. Okay, so we have a positive and also a negative root, and apparently the distance has to be positive. So we'll pick the positive distance 0.0351 right here. So that's roughly 3.5 centimeters of compression. So D equals 0.351. Sorry, 0.0351. 0.0351 meters, or if you want centimeters, 3.51 centimeters. Okay, so that was how much initially the spring was compressed, and you can also find out how fast the ball came out of the spring launcher, since you have this already. So we have E2 here. E2 equals E1, and E2 has this, so 1/2 m V2 squared plus mgd equals 600 d squared. So 1/2 mv2 squared is equal to 600 d squared minus mgd, and then V2 is equal to 2 over m 600 d squared minus mgd. Then we take the square root of this whole thing. Okay, let's use our calculator. Now 2 over m, so 2 over 0.015 times 600, and the d was 0.0351 squared, minus mass is 0.015, g is 9.8, then a d of 0.0351. And then we also take square root of that number. So let's check for mistakes. 2 over mass, okay, that's 0.015. Pretty sure I struck the 0, but it's a wireless keyboard. So 600 times 0.0351 squared minus 0.015 times 9.8 and 0.0351. Okay, that looks good now. So we have a speed of 9.89 meters per second. So 9.89 meters per second. Thank you.